In this video, we're going to do the coordinate covalent compounds and the ion exceptions. So the 3 coordinate covalents that we need to know. And then there's some ion exceptions that are also, they're pretty easy. So let's start. So when you have an ion in a molecule, what it's really saying is this -1 here, it could be a positive, but the -1 is saying that you have an extra electron. Just like if an atom had a -1 charge, it means there's an extra electron. So basically what you do, and this happens a lot, is you're going to bond it up, and then you're going to be 1 bond short. That's where the extra electron comes in. Look at the most simple example. So when I bond O to H, and again, this is saying you have 1 O and 1 H, not as many as you need to make it stable. You just get 1 of each. And so when I bond this, I know oxygen has 6 valence, hydrogen has 1. I bond it. Oxygen's not stable. It needs 1 extra bond, but it doesn't have an extra atom. That's where the negative sign comes in. It means you have an extra electron to put where you need. I used a red X. And so when I do my Lewis dot, it looks like this. The name for this shape still linear diatomic. Now, when does this happen? Why does this happen? This happens when chemical bonds form and there's a limited amount of extra atoms, or there's not enough. Normally, when H and O come together, they typically make water, but in order to do that, you need 2 hydrogen. Well, what if you had H and O together, but there literally wasn't twice as much H as hydrogen? They were just in a 1-to-1 ratio. Well, they'd end up forming something like this if they could at least grab an extra electron. So these are specialty circumstances. They don't happen very often. Well, frequently, but not not all too common, but frequent enough for us to talk about it. And so that's why we're mentioning it. So CN, same thing. Carbon normally 4 valence. Nitrogen has 5. Carbon will normally want to make 4 bonds. Nitrogen can only make 3 because once nitrogen gets to 3, it's stable, it stops. So carbon would normally need an extra bond. It would usually bond to like an H or some other molecule, but in this case there is no other molecule. That's where the negative sign comes in. There's the extra electron, it goes there. So it's basically like carbon had 5 valence instead of 4, and then it only needed to make 3 bonds. It's pretty much adjusting it. Name of shape. Linear diatomic. Now, coordinate covalents are a little different. They don't have charges. Well, they don't have negative charges. So what ends up happening with a coordinate covalent is this. So you start out with the base molecule, which is going to look like this guy, which is going to be NH4. So I'm just going to draw out the final version because we're going to save some time. No, I'll do the whole thing. So there's my molecule. And then you have an H+. Now, in order to be a molecule, the fact that they're all in one chemical formula is saying not this. In other words, this H can't be separate from the rest of it. So here's what happened. Hydrogen lost its electron somehow. Some atom was strong enough to rip it away, or something happened where it lost an electron. So now you have a random hydrogen floating around, and it doesn't even have a single electron. It is very unstable. It does not want to be this way. It wants 2, but it doesn't have any. So here's what it does. It says, wow, there's a lone pair here that nobody's using. Now, granted, nitrogen's using it, but not to make bonds. So it's just this lone pair just hanging out. Well, what does the hydrogen do? It basically jumps onto the back of the nitrogen and forces a bond to form. So the way we show that, we can't show it the same way as a regular covalent bond, because then we wouldn't know that there's something different about it. So what we do is you draw the bond as an arrow like that. I'm not going to put in polarity arrows, it would be too much, but it would look like that, and I just made it red. It doesn't have to be. So you just use an arrow like that to show that this bond is a coordinate covalent bond. So it's covalent, but it's not a normal style of bonds. It's basically one atom is supplying both electrons to the bond, which does not normally happen. And so this is a very unstable bond, but basically having hydrogen be separate is worse than having hydrogen be, attached to the back of nitrogen where it shouldn't be. Okay, and so this is still a better scenario than this, but if anything else comes along where this hydrogen can get a better deal, like its own electrons, that it doesn't have to borrow two from somebody else, this hydrogen will pop off and go that way. And so that makes these molecules very unstable, but they are very useful for us. This is ammonia. It's used in cleaning supplies. That's why when you clean, when you clean your bathroom using stuff that has this, you're supposed to leave the windows open. It really kind of burns your nose when it stings. It's not good to breathe in for that exact reason. It's this hydrogen that makes it a great cleaner, because it can jump off and attack bacteria and viruses and take electrons right out of their cell wall and things like that. But it's also what makes it not great to breathe in. Name of shape. When it's like this, it's tetrahedral. Next one, oxygen can do this too. So we have the exact same scenario happening. Oxygen has two lone pairs. We have a hydrogen without any electrons coming along. It really wants some electrons, so it jumps onto the back of the oxygen and it forms H3O, which looks like this. Now, a lot of times you will see them not drawn this way. They'll just make it a regular bond, because chemistry tends to be a little elitist, and they say, oh, well, anyone who sees H3O with an oxygen with 3 bonds automatically knows this is going on, so I don't really have to draw it out like this. You do. You're not that advanced yet. But that's pretty much the way it works. And again, same thing. This H will pop off. Any chance it gets to, the moment it gets a better deal, it'll jump off and take that deal. But it's still, this scenario is still better than regular random H with no electrons. Name of shape. Pyramidal. And then the last one, this one's a little different. It's not done the same. It's carbon and oxygen. So carbon makes 2 bonds. But now carbon needs to make 2 more. So normally it would find another oxygen, but there isn't another oxygen. So what does it do? Well, it's super unstable, but in this case, oxygen can actually donate both electrons to the bond. And so you end up with that, which is called carbon monoxide, not carbon dioxide. And this actually is a pretty important molecule, because every year people die from carbon monoxide poisoning, because what happens is when the temperature goes down, obviously it gets cold at night, and this time of year, the heat kicks on at night, and what will happen is people's furnaces will have soot build up, and that soot will build up and restrict the oxygen flow into the furnace, right? And when that happens, you now have carbon-based fuel being burned with not enough oxygen, and instead of making CO2, which would normally be the byproduct of CNO, since there's not enough oxygen to make CO2, you get just CO, which is carbon monoxide. And if that soot backup, that the backup, that's the same backup that's preventing the oxygen from coming into the house, is also preventing the CO from leaving. And then the CO backs up into the house, and that's how people die, because it fills the house with carbon monoxide, which we can't breathe. We physically can breathe it in, but it doesn't do the same thing as oxygen for our lungs. It doesn't provide our cells the oxygen needed for them to survive, and you end up dying from this. And one of the worst parts about it is, one of the symptoms of carbon monoxide poisoning is being tired, and this typically happens in people's houses in the evening when everyone's sleeping, when the temperature drops, because that's when the heat kicks on the most often. And so it does happen every year, and it's part of the reason why you have to keep a carbon monoxide, or you should have a carbon monoxide detector in your house, because in the winter particularly, this is when you're most susceptible to this. Name of shape. All right, and these are all the exceptions that we're going to deal with bonding, and that's it. It's literally going to be these three. There are no other versions, and it's going to be these two ions, and you're never going to have to deal with another ion or another polyatomic. Now, in terms of regular covalent bonding, yes, we can expand that, and we're going to do a lot more with that. But as far as exceptions, this is the 100% list of exceptions. There will be no more exceptions for bonding other than the ones I mentioned.